Okay, third session of the day, and we're on a rocking roll. Okay, traffic lights. So we're doing, the method of characteristics. We've got this conservation law. We've got a particular model which corresponds to cars, right? It's a model of cars. Actually, people use this sort of business when they actually try and model traffic. It gets a lot more elaborate, of course, because there's a lot more to take account of, but it's a real model that people in traffic engineering sometimes use. So, traffic lights. Let's do the green light to red light problem. So what's going on? We've got rho is equal to rho 0. For t less than 0, there's a traffic light at x is equal to 0. It's green for t is less than 0, so that means this lane of cars of constant density just happily moving along turns red at t is equal to 0. Okay. Okay, right, so what's happening now is the following. As soon as the light turns red, cars have to stop in this model. And so the t-axis here, that's where the traffic light is, it becomes an impermeable barrier. Right, cars can't get through. Crikey. Barrier. Okay. All right, so let's just consider the characteristics diagram a little bit. I'm starting to getting too small in my writing. So the characteristics diagram, all right, I'm starting to draw it down there. So we've got the characteristics information here. So we've got x0 plus t minus 2 rho 0 t if you start at x-axis. All right, and e.g., let's put rho naught as a half. If rho naught is a half, that means that x is x0. That's an easy one to draw, right? So what does that mean? Well, if I come over here, it means that there's a bunch of characteristics that are just vertical. And those vertical characteristics here, that's the direction in which information is transferred. The cars are actually moving that way at the original speed, which was 1 minus rho naught. Anyway, so we've got information that comes up here from the initial condition. The initial condition is that. Right, so that's when you start on the x-axis. However, we've now put a wall here. So really what we've done is we've now said, okay, well, we've got a problem on this side and a problem on this side, and they're no longer communicating with one another. All right, I really should be putting a boundary condition there. And for the cars on this side, right, the minute that you turn red, these cars continue in that direction and they leave nothing behind. So on this side, we really should be putting a boundary condition on at the traffic light, which is that rho of 0 and t is equal to 0. That's okay. So let's just put that but for x greater than 0 problem, we have that rho of 0t is equal to 0. Okay, well, what does that mean? It means that if I think about my solution, the initial condition is sort of like the following. So this is rho. I have rho 0 everywhere to the right, but then I've got the point that x is equal to 0 is equal to 0 because nothing's coming through. So we've got a step there. In fact, at this stage, the problem looks awfully like the pileup problem, right? We had no cars behind, we had an initial ramp, then we had a lane there, and that steepened up and became vertical, at which point we had no cars, we had cars of rho naught, and we had this discontinuity. This is exactly what we've got here. So we've got the same shock as in the pileup problem. And in fact, everything's the same, right? And we've got the value on the left is 0, the value on the right is rho naught. That's what we had in the pileup problem. So we can just immediately say that we have x star, that's the position of the shock, it equals, the speed was 1 minus rho naught, given the values on either side, times time. And then we had an integration constant from here, integrating that. And the integration constant in this case is 0 because the shock at t is equal to 0 is at x is equal to 0. So there's the shock. All right, so I'll come along here. What's going to be the best color for the shock? Let's put it pink, I suppose. So there's going to be some shock here. X star is 1 minus rho naught t. There it is. Happily trundling along. And obviously all of the characteristics on this side are just going to come up and hit the shock and get consumed by it. And that way we don't have any possibility of getting a multivalued solution. Now, above here, the characteristics are not going to come from the x-axis anymore, they're going to come from the t-axis. All right, we're going to have to say that our characteristic equations have got a slightly different solution. We don't have that anymore. X is going to be, right, so there's no x0 now, it's going to be t minus t0. If I'm going to start at a position there, that's t0. And rho along here is 0. So it's x is t minus t0. The coefficient is 1. I've gone overboard with the amount of space I left for it. Those are all of the characteristics from this side. So now I'm going to draw those. Now doing something like that. So that's the solution on the right. We've got this shock that continues. We've got this consumption of characteristics from either the initial condition or the boundary condition. Right. What happens on this side? Right. You know, if I think about what the cars are doing here, all right, I've just got this lane of cars that are happily moving along. Right, there's a sudden cliff at the back going from the constant density of the lane to 0, and that just happily moves off at this particular speed. Right, so that's on the right side. Let's go to the other side. Okay, so at the back now, we have a different kind of boundary value problem. So the cars, they're still coming this way. However, they can't get through. So there can be no cars moving through there. So here we have to have the car speed is 0. And if I remember what the car speed it was rho times the car speed here. So it was 1 minus rho. So that means that rho is equal to 1 there. The boundary condition is that rho is equal to 1 here because the cars immediately have to brake and jam up so that they're not moving anymore. That demands that that's what I get there. Right, so let's just sketch that. Right, so there's the stoplight. That means that we're coming in originally at rho is equal to rho 0, but then I have to immediately jump up to the point there, which is at 1. Right, so we get another discontinuity, another shock from rho minus equals rho 0 and rho plus is 1. So coming back there, that means that dx star dt is equal to 1 minus 1 minus rho 0. That's minus rho 0. So I can immediately write this as x star is minus rho 0t. So now there's a shock here. That's coming up this way. Ooh. That should be a straight line. X star. Oh. These pens are getting kind of thickish. I must be pressing on too much. How's that look? That looks okay. Now, once again, that means that I can continue all of these characteristics. Wrong colour. Up to the shock. Like so. These get consumed by the left moving shock. And I can also do the same thing on this side. All right. So above the shock, that's for t greater than x star. I need to revise my characteristics. It's t is equal to, x is equal to, so it's t minus t0, and it's 1 minus 2 rho, but rho here is equal to 1, so that's t0 minus t. Right, so I start a point there, this comes up there and hits the shock, like so. Right, so I get consumption of characteristics on both sides, 2 shocks. That's what the characteristics diagram looks like. And if I wanted to just sketch the solution, I could do that as well. I may as well. So this is x, there's the traffic light. My solution on the right consists of a jump from 0 up to rho 0. That is at x star is equal to that thing, 1 minus rho naught t. And then on the other side, I have rho 0 way back that jumps up to 1. That's the same value. And this position, that's x star is minus rho naught t. Right, so as time progresses, these discontinuities just move off like that. So that's what it looks like. That's the green light, red light problem. Okay. Ready? Let's do another one. So let's do the opposite. Let's now do the red light to a green light. So the previous problem and the pilot problem, it was all about shocks, right? It was all about shock steepening, discontinuities forming, and looking at the motion of the shock. we have this nice equation that tells us the shock speed. So the red light to green light problem is a bit different. And if you think about it a little bit, you'll kind of realize why that would be the case. So let's just set the problem up. Let's set the stage. We have stationary traffic for x less than 0, and then released at t is equal to 0 when the light changes by red light turning green. So that means that I've got an initial condition which is a step function. It's actually h of minus x, right? V is 0 implies that rho is 1. And that's a step down, so that's our initial condition. Okay, now in this particular problem, right, I've got high density of cars at the back, and then when I go down the step, there are no cars in front, and so you would naturally expect that the cars at the front can happily accelerate away, whereas the cars at the back can't do anything, they're still jammed up. Right, so we've got this step down. The stuff here has to stay where it is to begin with. The stuff at the front is able to go right. So you kind of expect that the step to smooth out. That's not a shock at all. Okay, so we've got a discontinuity. However, you sort of think that as soon as you release the cars and we have a finite time, t is not 0, there's no discontinuity anymore. So let's just try and elaborate on that by avoiding the step. Let's avoid that by smoothing it out a little bit. So let's change this. So we'll go from minus epsilon to plus epsilon, and we'll put 1 here, we'll put 0 there, and then we'll have a little bit of a ramp again. Ramps are easy to deal with because we can get nice analytical solutions of this particular problem. So rho in this particular case is going to be 1 if x is less than minus epsilon. It's going to be 0 if x is bigger than epsilon. And then we'll just put something in here. So it's going to be 1/2 and if I put this as the middle branch for the ramp, then it achieves what we've just drawn. So let's check it. When x is equal to epsilon, that's 0. And when x is equal to minus epsilon, that becomes 1. Right, so there it is. 1, ramp, 0. Okay, so if I go through and I use my solution, right, this is f. That's rho of x and 0, f of x. And we have that rho of x and t is f of x minus t plus 2 rho t. There's the implicit solution, but I put this in there. And for the middle part, I can then solve a linear equation, and I get the following. I get rho is equal to 1/2 epsilon minus x plus t divided by t plus epsilon. Right, so that's the middle section. Right, so actually this is the initial condition, right? So this is f of x0 when I'm solving it with characteristics, and so these x's are all x0s. So this is 4 minus epsilon x0 there. Now let's just do a side calculation over here to find out where that is in terms of x. So when I put x0 equals to minus epsilon, then rho is equal to 1. That means from here that x is equal to minus epsilon t minus 2t. So minus epsilon minus t less than or equal to x, that's on the left side. And then if I put x naught is equal to plus epsilon, rho is equal to 0, so x is equal to epsilon plus t from there. So there it is. Right, so that's what we have, and we've got that rho is equal to 1 for x is less than this thing, and rho is equal to 0 for x is bigger than that thing. So that's the solution, that's the explicit solution. Right, when we've cheated slightly by replacing that by that, obviously what I would like to do is I'd like to take this solution and then slowly make epsilon get smaller and smaller so that then we can limit this problem to that problem. And then we can understand more generally what must have happened to the jump in the initial condition. Okay, so let's draw this as a characteristics diagram. By now you'll have appreciated the fact that we get a lot of insight from plotting the characteristics. Okie dokie. So, characteristics diagram. Here it is. T and x minus epsilon plus epsilon. There's the ramp. On the right here, we've got rho is equal to 0. That means that x is x naught plus t. On the left here, we've got rho is equal to 1. That means that x is x naught minus t. And then we've got the ramp in between where we tilt over from there to there. So we get this kind of fanning out again. So we get something that looks like that. And as in the problem that we discussed a while ago, you know, when you have a thing that looks like that, what's happening is that the original step is a step down in this case. Right? There's the step down, the information of the points on there is being moved apart by the characteristics. Better stop using the blue. So if I now draw the solution here, I'm starting with the step down. Then what's happening is that the points are retaining their values of u, but they're moving apart. So at later times, I get something that looks like that. Right, the step gets shallower. The ramp gets shallower. All right, so that's what's happening. We get this rarefaction, right? So coming back over here, now let's perform the exercise that I mentioned before. What we're really interested in is the limit where this thing comes together, and we had a step to begin with. If I come down here, what that means is that my rho is equal to 1 if x is less than minus t. It's 0 if x is bigger than t. And looking at this, if I throw away the epsilon, I get 1/2 1 minus x over t. So this is when let's manufacture a bit more space there. That's when x is between minus t and plus t. There it is, that's the solution. Right? It looks like this exactly, except these points have now moved together. So we start with the step, but then it tilts over in just the same way. What about the characteristics diagram? Well, it's exactly the same, except now these points have come to zero, to the origin. So we've got the characteristics on this side. We've got the characteristics on this side. And we've got the ramp here, but now it's all shrunk to a point. So instead of fanning out from a finite section of the x-axis, all of the characteristics pop out of the origin. So we've got this wedge section here, and we've got these regions here. So we've got region A, B, and C. Okay, so that's exactly what happens when I take the limit. Okay, at this point, I'll just mention a few things, a bit of terminology. So I've got a fan here, right? Really looks like a fan. So people call that an expansion fan. So I've got A, that's where rho is equal to 1. B, that's where rho is equal to 0. C, we've got that rho is equal to 1/2 1 minus x over t, and this is called an expansion fan. And what happens is that you see exactly what we talked about to begin with, which is that my initial step, let's just quickly redraw this. So this is with epsilon going to 0. I start with this, the step, but then immediately what happens is that it tilts over like that. Right, so that's u against x at different times. So that's the expansion fan. Now, you might think, well, we took a little bit of a roundabout route to get to this solution. Right? We had to first of all replace this problem with that problem. Is it possible to avoid doing that? And the answer is yes. So how do you do that? So here's a quick argument that allows us to skip putting epsilon in and then making it get small. So the key observation is that all of the characteristics in region C, they all come from the origin. So what does that mean? If I come back to my characteristics solution, I have this handy relationship here. And if x0 is 0, because everything's coming out of that particular point, lo and behold, I can solve that for rho. So in region C, the fan, x0 is equal to 0. Therefore, x is equal to t minus 2 rho t, or if I solve this, I get that, which is exactly what I found by the limiting process. So I get it regardless. I get this regardless of the limiting process. Okay, and that's what's going on down there. Okay, so that's the red light to green light problem. Now let's jazz it up a little bit. So when the light turns, you get an expansion fan. How am I going to jazz this up? Well, let's make the lane of traffic that's sitting at the traffic light finite. Let's say it's got a finite length. What happens if we've got a finite length? So there's a back. And everything we've drawn so far, it kind of had an infinite tail off to minus infinity in x. So we're going to change that now. So let's do the finite lane. So what does that mean? It means that rho is equal to 1, but only between, let's call it minus L and 0, ahead and 0, and behind it's 0 as well. So that's my initial condition. Let's just draw it. There it is. Right, so that's my traffic. Okay, well, what happens in this particular problem? Well, to begin with, you kind of look at this thing and you think, well, okay, I'm going to have the release of the cars at the front, and they're going to move away, leaving the ones behind. I should get this expansion fan at the front. At the back, I've got one of these steps up. Right? A step down turns into an expansion fan, a step up stays as a shock. And I'm going from 0 to 1. So if I'm going from 0 to 1, that means this shock here just stays where it is. So we've got a fan at the front for t greater than 0, and a shock at the back. And x star, or d by dt of x star is 0, so x star remains as minus L. Okay, quick characteristics diagram. Right, there's minus L. So I know that I have rho is equal to 0, rho is equal to 0, and then I've got my thing here which turns a little step down, which turns into an expansion fan that I just drew. There's the fan. And these characteristics are just parallel to the last one on that side. And then they're the same slope on this side. So they look like that, and there's a shock here. There's the shock. And now over this region, that's where I've got 1. And let's just put in that's x is x0 plus t. That's what happens here. Over here, that's where rho is equal to 1, so that says that x is x0 minus t, so they're all parallel to this one. So they're coming in like that, and they hit the shock from that side. Okay, so that's what the picture is so far. Now, of course, I can just continue these up a little bit further. That one hits there. This one, at some point, will hit the shock too. So I get that. This thing's going to continue up like this. These things are still spreading out, like so. So, at this point, what happens, this is the wrong way of saying it, but the shock hits the fan. Right? It's actually the fan hits the shock. But it's better to say that the shock hits the fan because it sounds more dramatic. So let's put that on there. Here, the shock hits the fan. What happens then? Okay, well, at that point, I should maybe perhaps draw the solution. That might be a good idea. Okay, so here's the solution. So this is going to happen at a certain moment. Let's call this TF. So for T less than TF, then what's happening is that I've got one stationary shock and an expansion fan. And then as time's gone on, this thing's tilting over more and more, eating into the traffic, and at some point, the shock hits the fan. Right, so that's what happens before that particular moment. And afterwards, what's going to happen is that the front of the shock corresponds to the fan. So that means that rho plus is in the fan. Now, when we did the calculation for this, right, we had that rho minus was 0 and rho plus was equal to 1. That's not true anymore. So, in fact, what you'll see is that if this tilts over anymore, the value at the front is less than 1. If it's less than 1, that thing's not 0 anymore, so the shock will start to move. Right, so when the shock hits the fan, we get a mobile shock. So when the fan hits the shock. Better way of saying it. Okay, so let's deal with that situation. So the good thing is that when we're down here, when we're bigger than this time TF, then we do have an explicit expression for the value of rho in the fan. Let's just write it down. That's what we derived in the last problem. What we have in particular is that in the fan, we've got that rho is 1/2 1 minus x over t. So that means that rho plus is equal to 1/2 1 minus x star over t. So let's throw that into here. So we've got dx star dt equals 1. Rho minus is always 0. The values on the left are 0, but we've got minus this. That's a differential equation for the shock position, rather charmingly. So dx star dt minus 1/2 x star over t is equal to 1/2. That's the equation for the shock position. It's a nice ODE for it. I should stop using that pen. And I've dropped one. There it is. Okay, so let's solve that. Up there. The way to solve this is it's a linear first order equation. There's an integrating factor. Doesn't get any better than that. So I realize that the integrating factor here is going to be from integrating that and exponentiating. It's actually t to the minus 1/2. So if I multiply by t to the minus 1/2, I turn this equation into that nice derivative. And so t to the 1/2 x star is equal to, if I integrate that, that's t to the 1/2. Now I've got an integration constant. What's the integration constant? Well, okay, I have to bear in mind that at t is equal to tf, x star is equal to minus L. Right? So I can now choose that. It's t to the 1/2 minus tf to the 1/2 minus L. That puts the shock here when it starts to move. Okay, great. I guess I should first of all figure out what TF is in order to press any further. So the back of the fan, that was when x was equal to minus t. That position there is minus t, and that was plus t. So that implies that TF is equal to plus L, since that position is minus L. That's when the back of the fan hits the stationary shock. Okay, so X star is equal to 1 minus I forgot that my constant's not quite right. So when T is equal to TF, I've got to get that. So this is L times TF to the 1/2, right? So this is 1 minus T. Oh yeah, I've done something wrong here. Because the answer should be T minus, oh, that's because I forgot the minus sign here. Ah, that's more like it. So T to the 1/2, I integrate that to get this. So I have to get a minus sign there in order to get the initial condition right. Yep. So when T is equal to TF, that's 0. There's a TF to the -1/2, TF to the -1/2, and I've got minus L for X star. Right, there we go. Okay, so coming down here, I was about to write out the answer. So we get X star is equal to, I just need to put L in there, and I realize that I've got, having divided by that, it's T minus LT with a square root. And none of that are the same, so I end up with a 2. That's for T greater than L. Okay, so that's now what I've got in my notes. Good. Okay, so now this thing's now going to be eating into the shock, but the shock's going to be moving at the same time. I guess I can translate this over here, because what I would like to do finally is to complete the characteristics diagram, which is going to be useful if I can draw further up. Okay. Okay, so now, with delicate artistic sensibilities, we're going to push this thing up. So what happens? Well, if I look at the form of this, for large values of time, when t gets big, that's t to the 1/2. So this is going to be much bigger than that. So ultimately, I'm going to get to a line where x star is t. And that's actually the same as lines like this. All right, so this thing is going to have to bend over and then reach an asymptote which is parallel to those characteristics. So it's going to come up, it's going to start to move, and tilt over and start doing that. This is parallel to those and those. So that's what X star is doing. And at the same time, I can now launch into it all of these characteristics from the left, the ones from the fan. Now I can just carry on going and hit from this side. And there's not much point in drawing anything on there. I guess I can put another characteristic in there. And there. So that's what it looks like. And for later times, I guess I can draw the solution. Let's just do it once. There was minus L. All right, so the initial condition was something like that. At some later time, this thing's tilted over a long way, but this position has shifted that way. So this is now X star, and it's gone up there, and there's this ramp. That's the remnant of the expansion fan. So that's what U looks like for T greater than TF, which is L. Okay, so that now completes our discussion of traffic flow problems. Whew, very pretty. Let's take a slight break.